By now we know that the state of stress at the given site is composed by four main quantities: the vertical stress, the two horizontal stresses, and pore pressure. Particularly for horizontal stress, we haven't talked much about what is the reason for such value or how we can predict or calculate those horizontal stresses. In order to do that, we need more tools, more mechanical and mathematical tools in order to explain that. And we're going to see this in chapter number 3, and we'll see that these tools will also allow us to calculate some other stresses which are important to us, like for example, stresses around a wellbore or stresses around a fracture or change of stresses in a reservoir when the pore pressure changes. So let's start with the fundamentals. And this is what the stress tensor is. And let's start here with an example in order to explain what the stress tensor is. Okay, first of all, let's consider this case, which is meant to be in a schematic of an unconventional formation at a given depth with a horizontal wellbore and vertical hydraulic fractures. All right, at this particular site, we could measure, for example, the pore pressure or the temperature. The value of pore pressure is just going to be one single number because it is a pressure. For example, in this case, if we assume this under hydrostatic conditions, we know by now that the gradient is about 0.43 or 0.44 psi per foot. So if I am at 10,000 feet of depth, the pore pressure is going to be 4,300 psi. It's just one value, and it's independent on the coordinate system you refer to. Here we have two examples: this coordinate system NED and this coordinate system XYZ. It doesn't matter which coordinate system you use, the value of pore pressure is going to be the same. And it's the same with, for example, temperature or porosity. You just need one numerical value in order to define these quantities. This is what in mathematics are called scalar quantities. They are independent of the coordinate system. It's just one number. All right, let's go to another case which is a little bit more complicated, and this is the case of a vectorial quantity. In a vectorial quantity, we have a magnitude and a direction. And if you want to write that mathematically in a given coordinate system, in particular in a three-dimensional coordinate system, as the one that we're going to use in our application problems in geomechanics, then you will need a vector with three values. Let's see, for example, this case of this vectorial quantity, velocity. In this case, I'm referred to fluid velocity. For example, if you have here a given point in reservoir and you do a fracture and you start lowering the pressure in the fracture so that the fluids move into the fracture, from the rock into the fracture, well, the fluid is going to move at a given velocity. And in this example, notice that this value of velocity is going mostly in direction from the east to the west, and with according to this coordinate system that here I have defined as with first element the north, second element the east, and third element depth or direction down, the movement is in direction of the axis number 2. So when I write this vector with three values, then it's going to be 0 in direction of the north, -1 in direction of the east because it's going against the direction of the element of the base, and 0 in direction of the depth or down because it's not moving up and down. So you can see that now with these vectorial quantities, we need these three numbers to fully define this vector in a three-dimensional space. A similar case happens with this vector of displacement. imagine that here, when we do a hydraulic fracture, the rock is initially placed in a given point, but after we open a hydraulic fracture and we prop it, it displaces a given amount. This tiny vector over here now is moving to the right in the paper, but according to our coordinate system 1, 2, 3, or any d in here, this is moving towards the east, so now it's going to be a positive value. Okay, so we are familiar with these quantities, scalars and vectors. You have seen these in probably already in high school and already in some other courses here in college. But probably what you haven't seen yet is what a tensor is. Particularly for me, I got to know about tensors in my last year of college too. So let's see what a tensor is. First, let's make it easy. We went to one number to three numbers in 3 dimensions, and now the tensor is going to be 9 values in order to define a particular condition or a particular physical characteristic. Notice that we have related so far all of these quantities to physics, like a pressure, like a velocity. Well, now we're going to relate this new quantity, which is going to be stress, to a tensor. And what is a tensor? Probably, don't be confused about that. Unlike this meme over here, it's not as complicated as it looks like. The tensor is just going to be a higher order mathematical entity in order to describe a physical quantity. And in this case, this is going to be a stress. Again, scalar, vector, and then a tensor, and now we need a matrix. And notice why we need a tensor. When we talk about the state of stress at a given site, in order to fully define that state of stress, just to begin with, we need 3 different values, which are what we're going to call the principal stresses. And in this example are the stresses maximum horizontal stress, minimum horizontal stress, and vertical stress. Those 3 values in general are going to be independent at a given point. So there we have already 3 independent variables. But notice that also those stresses are going to have a direction similar to a vector. And the direction is going to define, or is going to depend on the directions of these 3 principal stresses. So now it's not like the vector that we just have one direction. For the tensor, we need 3 directions. So in addition to the 3 value of stresses, in order to fully characterize the stress state at a given site, we need 3 directions. So that makes 6 independent variables. And I told you that this was 9 because we have a 3 by 3 matrix. Well, good news, these tensors are symmetric. The elements, there's a missing 0 over here. The elements in the diagonal are going to be, in this case, the principal stresses. We're going to talk a bit about that in a minute. And the off-diagonal terms, again, there's a 0 missing over here. The off-diagonal terms are going to be equal on either side of the diagonal. So at the end of the day, we just have 6 independent values. 1, 2, 3, 4, the missing 0, 5, and 6. If we were to write this as a matrix. If we see the physical representation then, and we think about principal stress and principal directions, we need 3 independent values of the principal stress and 3 additional independent directions for those stresses. All right, so the tensor then is just going to be a mathematical way of represent something which is more complex than a vector and requires more values in order to define it. And let's see a little bit more about the properties of these tensors. The tensor in general is going to be composed, as you were saying, by 9 values, from which 6 are independent. And in this particular case that I have written here, I have assumed that these are the principal stresses. What that means is that I just have normal stresses on that element and at that particular condition, and the shear stresses, which are the off-diagonal terms, are equal to 0. I'll come back to this in a minute to explain that in detail. But let's see what would be the case without shear stresses. In general, when these principal stresses are not aligned with the coordinate system, for example, in this case, my principal stress, I assume that they are aligned with the direction of north-south, east-west, and the vertical direction. That's why this tensor just looks very simple with zeros in the off-diagonal terms. If I were to write this tensor in a different coordinate system, like this coordinate system x, y, z, then the stress tensor is going to have all the elements which are non-zero. And in general, I'm going to define those as S11, S12, S13, and so on, where the first index is the row and the second index is the column. In general, as I was saying, these 9 elements are going to be non-zero values from which 6 are independent. Let's come back to the principal stress case. When I am in the coordinate system of principal stresses, I have no shear stresses, and we'll see the physical interpretation of that in a minute, and just the diagonal elements are non-zero values. And these are what we call the principal stresses. In this particular example, just to finish the example, I have put some typical values for stress. Remember that onshore, a typical gradient for vertical stress is 1 psi per foot. So if we are at 10,000 feet, then we're going to have 10,000 psi for the vertical stress, and a typical value of maximum or minimum horizontal stress in a normal faulting condition would be about 70%, or in an unconventional formation, maybe a little bit more, of the vertical stress. So my minimum horizontal stress here is 70% of the vertical stress, which is 7,000. And since the maximum horizontal stress is a little bit higher, then I have assumed that this value is 7,500 psi for this case. One more thing to notice in this case is to notice that the position of the elements or the variables within the tensor. SH max aligns with the direction of the north. And this is what I have here in my physical representation as well. SH min aligns with direction east-west, which is the second element, and that's why it's located second. And third, the vertical stress is aligned with the third axis. That's why it is in location 3, 3. All right, so let's see a more general representation of a stress tensor. And it looks more or less like this, where now we have this stress tensor, and it is drawn according to this coordinate system 1, 2, 3. Something very important to mention here is that we are always going to use a right-handed coordinate system. And this coordinate system in 3 dimensions, when it follows the right-hand rule, your index finger is going to be element number 1, your middle finger is going to be element number 2, and your thumb is going to be element number 3. So you can check on your own now, just with your right hand, try to follow the coordinate system that I have in this particular figure, and if you align your fingers with the directions of the axis, you will see that they follow this rule. If you do this with your index finger pointing into the screen, the middle finger pointing towards the right, your thumb should be pointing down and should be aligned with this coordinate system. Okay, when we write the stress tensor and we make the physical representation of this stress tensor with such coordinate system, we're going to find that we're going to be able to interpret what are the components of this stress tensor. Let's start with the easy ones. The diagonal elements, S11, S22, and S33, in physical interpretation are going to be normal stresses on the faces of this Cartesian cubic element in order to represent stress. So normal stresses, that means that those stresses are perpendicular to the plane in which they are applied. And also the subscripts, they refer to orientations. For example, S33 means the stress applied on face number 3 on direction 3. Which is face number 3? Face number 3 is the face which is perpendicular to direction 3, which is this face. The easiest way to define a plane is by defining the normal direction to it. So in this case, this is face number 3. Here, this is face number 1, and this one is face number 2. And going to this example, this is a stress applied on face number 2 on direction 2. And therefore, that makes it a normal stress, perpendicular to that face. These normal stresses can be compressive or tensile. Usually in geomechanics, we use the convention that compression is positive and tension is negative. Okay, these are the normal stresses which go in the diagonal. Let's see now the shear stresses, which are the off-diagonal terms. The off-diagonal terms are shear stresses, and they follow the same convention as the normal stresses. Let me zoom in a little bit more. Let's start with this one, S12. S12 is the shear stress applied on face number 1 oriented in direction number 2. S13 is the shear stress applied on face number 1 but in direction number 3. So now for a given face of this cube, I have 3 stresses, 1 normal stress and 2 shear stresses, and it's the same for the other ones. And again, these shear stresses are going to go in the off-diagonal terms of the stress tensor. Let's say one more thing about this stress tensor, and this is about the convention of the direction of the arrows. In geomechanics, we assume that compression is positive, and as you may picture from this particular schematic, this element is being compressed because the normal stresses are pressing against the surfaces of the element. So these stresses is pushing from right to left, and in order to be in equilibrium, although it's not drawn, there should be another stress on the other side or on the other face too, so it is under equilibrium. So this is going to be under compression as long as the normal stresses are pushing against the element. If they are pulling out of the element, then that's going to be a tension, and that's going to, when we write it as a numerical value, is going to have a negative numerical value in the stress tensor. With the shear stresses, it's something similar, and it follows the same convention as the normal stresses, but it's a little bit more difficult to see. So before we go to the shear stresses, just notice the following. The normal stresses follow a convention that whenever they are on the positive side of the element, on the positive face, the vector points in direction opposite to the element of the base. Let's try to dissect what I just said. which is a positive and which is the negative phase of this element. The positive phase, like in this case, this phase 2 positive, is the phase that I find after moving a positive amount. If I move along direction 2 and I go from here to there, I may go, for example, from 0 to 1. 1 minus 0 is 1, it's a positive amount. If I were to go from 1 to 0, 0 minus 1, that's going to be a negative change. All right, let's go with the positive. So if I walk from here to here, I go in positive direction. And it's the same with the element. If I walk from here to there, I get to the positive phase. This is the positive phase number 2. And in the positive phase, I'm going to have my stress pointing opposite to the direction of the element. If I were to be in the negative phase, like for example, this is negative phase number 1. Why? Because in order to get to that, I need to walk a negative amount or a negative change, walking from here to there. And if you see the coordinate system, this is walking against the direction of the element of this base. Therefore, if I move a negative amount, I'm going to get into a negative phase, and in the negative phase, the direction of the arrow is going to be the same as the direction of the element of the base. So in negative phases, stresses, in order to be positive, they have to be aligned, or they have to go in the same direction as the element of the phase. And know that this is the case for S11, for S12, and for S13. And in the negative phase, they are in the opposite direction. S23 opposite, S21 opposite, and S22 the opposite too. All right, so for normal stresses, this is very important. For shear stresses, not that much. But for the convention of normal stresses, knowing what is compression and tension is very important. And again, let me remind you that in geomechanics, we assume that compression pushing against the element is going to be positive. All right. As we were discussing before, now that we know what is in general, what is in a stress tensor, we can come back to some of what I said before and we'll find the meaning for that. That any stress tensor, when it's written in any coordinate system with all elements diagonal and non-diagonal, which are different than 0, and with shear and normal stresses on the faces, any stress tensor can be converted into what is called the element of principal stress values and principal directions. And what that means is that this tensor is going to have one particular coordinate system or one particular orientation for which, if I write a stress tensor on that particular coordinate system, then the stress tensor is going to be written just with normal stresses in the stress tensor mathematically and 0 in the off-diagonal terms. And physically, that would mean that I just have normal stresses on the faces of the element and no shear stresses. So a principal stress value is going to be defined as the value for which I don't have any shear stress. Whenever I have a principal stress, that means that there is no shear stress in that particular plane. And this is very useful because for us, it's a lot easier to understand the state of stress in terms of principal stresses rather than in terms of the full stress tensor. And we have seen examples already about what are the principal directions. For example, let me pull the map that we have seen some time ago about the direction of horizontal stresses. And I'm pretty sure this is the one I'm looking for. Here, yeah, here we go. We see a map of the stress regime in the lower 48 states of the United States, and in addition to looking at the stress regime given by this label, we also see the direction of the maximum horizontal stress. So these black lines are telling me the direction of the principal stresses. In most places, vertical stress is already a principal stress. So we already know that one of the principal stresses. And the direction of this line is telling me the second direction of the second principal stress. And a property of these principal stresses is that they are all perpendicular to each other. So just by giving me, assuming that vertical stress is the principal stress, and if I know the other principal stress direction, like in this example SH max, automatically I know the direction of SH mean, because that's going to be perpendicular to this line. So in this map, then again, we see that not only the value of the stress is important, but it's also very important its direction. And that direction is going to be characterized by the principal stress direction. There's one more analogy I'd like to cite in this case about principal stresses. This is similar to the case of a vector. For example, if I come back to our first example over here, if I wanted to write the velocity or the displacement vectors in this case in the x, y, z coordinate system, I would need 3 values in order to write that vector. But if I use a coordinate system like this one, in which the vector aligns with the vector itself, you see that I only need 1 value and the other ones are 0. And it's very similar with the tensor. There is always going to be a coordinate system for which I can reduce a stress tensor with all its values different than 0, and physically that means with shear normal stresses, to a stress tensor in which I just have normal stresses and the shear stresses equal to 0. Okay, just a few more things about my notes here, just to complete the explanation of this. Here we see the derivation of the Cauchy equations of equilibrium, and this is now that we know what the stress tensor is and that we also have shear stresses, we can add up all the stresses in one direction, doing something very similar to what we did in this case to calculate the vertical stress gradient, but now we add also the shear stress terms. And when we do that, we get to an equation, a differential equation like this one, that if we extend to 3 dimensions, it looks like this. And with this general equation, we can solve more complex problems of continuum mechanics. This is basically your equation F equal ma for continuum mechanics. And we're not going to see in detail about how to solve these equations, but we're just going to refer to them later on as the equilibrium equations. And we're going to see some analytical numerical solutions to this equation, but again, we're not going to go into detail about what this differential means and how you get to solve them. I just have one example here of application about how to calculate vertical stress more rigorously than what we did in this case, and you get to the same answer, that after applying the equilibrium equations and just noticing what values are equal to 0, I can arrive to the equation of vertical stress as a function of depth if I have gravity. One more thing and last thing to say is that this is not the only equation that we need in order to solve a general continuum mechanics problem, but we're also going to need what are called the kinematic and the constitutive equations. The kinematic equations relate displacement to strains, and the constitutive equations relate strain to stresses and depend on the material properties. We are going to see these kinematic equations next, and we're going to see in detail what these constitutive equations are. Once we combine these three equations, the equilibrium equations, the kinematic equations, and the constitutive equations, we're going to be able to solve any problem of continuum mechanics.